Hello students, I am Ms. Ranita Pinto, Assistant Professor from the Department of ECE, SMVITM College. Today I will be going through the working principle of DC generator. As you already know, DC generator converts mechanical energy into electrical energy. So DC generator works on the principle that whenever a conductor is moved in a magnetic field such that it cuts across the lines of flux, dynamically induced EMF is produced in it according to the Faraday's laws of electromagnetic induction. So EMF produced is given by E is equal to B into L into V into sin theta. So where B is the flux density, L is the length of the conductor, V is the velocity, and theta is the angle between the conductor and the flux. So clearly you can see here it is given that the generator works on the principle of dynamically induced EMF. So we have already seen what is dynamically induced EMF in our regular class. So let us recall it again. So if the conductor is moving and the magnetic field is constant, then EMF will be induced in the coil due to the relative motion of the conductor and the magnetic field. Then such type of EMF is called as dynamically induced EMF. So one point to be noted here is, for the EMF to be produced, there always has to be relative motion between the conductor and the magnetic field. So if there is no relative motion between the conductor and the magnetic field, then no EMF will be induced. So here in the dynamically induced EMF, the conductor is moving, magnetic field is constant. Now let us see this dynamically induced EMF in detail. So I will consider a conductor. So I will consider a conductor of length L. So let L be the length of the conductor. Let B be the flux density of the conductor. And let me consider that this conductor has swept an area of dx in the time dt. So dx is the area swept by the conductor in the time dt. So dt is the time. Now we already know that EMF E is equal to d phi by dt. Now what is d phi? Now d phi is given by flux density into the area swept by the conductor in the time dt. So flux density into area will give me d phi. So what is the flux density? Flux density is nothing but B. So d phi is equal to B into, now conductor is of length L, so L is the length of the conductor into the area dx. So therefore d phi is equal to B into L into dx. Let me substitute this d phi in this above equation. Therefore you will get E is equal to B into L into dx by dt. Now what is this dx by dt? Now clearly you know that dx by dt is nothing but v, that is the velocity. Therefore I will get the final equation as E is equal to B into L into V volts. Now let me consider three different cases. I will consider the first case where conductor is moving at an angle theta. Second case, I will consider that the conductor is moving parallel to the flux. And third case, I will consider that the conductor is moving perpendicular to the flux. So first case, let me consider that I have a conductor and I have the magnetic field here. So you can see this magnetic lines of force. Now I'll consider that I have a conductor and this conductor is moving at an angle theta with respect to this magnetic lines of force. So let me consider that it is moving at an angle theta. Now this conductor is moving at an angle theta. It is at an angle theta with respect to this magnetic lines of force. So I can resolve this component into two different components. One is the cos component, another one is the sine component. So this conductor is moving with an velocity v. So the two components that is resolved is, one is the parallel component, one is the perpendicular component. So parallel component can be written as v cos theta whereas perpendicular component is called as v sin theta. Now let me see the parallel component. Now v cos theta parallel component is exactly in parallel with the magnetic lines of force. So therefore it does not cut any magnetic lines of force. Therefore because of this component no EMF will be induced. Therefore I can neglect this component. What about v sin theta? If you see this component, it cuts maximum lines of force. Therefore EMF will be induced because of this component. Therefore I can write that the EMF induced E is equal to B L V sin theta, where theta will be giving me the angle between the conductor and the magnetic lines of force. Next, let me consider the case of parallel, where the conductor is moving in parallel to the magnetic lines of force. So conductor is moving in parallel to the magnetic lines of force. So clearly again, the conductor will not cut any magnetic lines of force. It will not cut the flux. Therefore what happens? Theta will be equal to 0. So if I substitute theta equal to 0 in this above equation, E is equal to B LV sin theta, what happens? Sin 0 is equal to 0. Therefore E will be equal to 0. No EMF induced. So if the conductor is moving in parallel to the magnetic lines of force, in that case EMF will be equal to 0. Let me consider the third case, perpendicular, that is the conductor is moving perpendicular to the magnetic lines of force. What happens in this case? The conductor will cut the magnetic lines of force. Therefore, EMF is induced. Now, in this case, theta is equal to 90 degree. So, substitute theta equal to 90 degree in the above equation, that is E equal to B into L into V sin theta. Therefore, what happens? Sin 90 degree is equal to 1. Therefore, EMF induced can be given by E is equal to B L V. Therefore, we have different cases here. According to that, dynamically induced EMF can be given by the equation E is equal to B into L into V sin theta. So, if the conductor is moving parallel to the magnetic lines of force, therefore theta will be equal to 0 and no EMF will be induced. Suppose the conductor is moving perpendicular to the lines of force, therefore theta will be equal to 90 degree and maximum EMF will be induced. So this is the working principle of the DC generator. Now, we all know that the EMF causes the current to flow in the conductor. So electric power will be developed. So if the conductor is moved parallel or if the conductor is stationary with respect to the magnetic lines of force, then no EMF will be induced, so no power will be generated. Therefore, clearly we can come to the conclusion that for the EMF to be generated, there has to be relative motion between the conductor and the magnetic field. Now, in a practical generator, we have three different requirements. One is the conductor, then you have the flux and the relative motion between the conductor and the flux. So I have already told you, only when there is a relative motion between the conductor and the flux, there will be EMF induced. Now, in the generator, conductors are rotated to cut the flux. So, to obtain a larger output, what happens is you need a several number of conductors, and all these conductors should be joined in a particular fashion, forming a winding. So this winding will be placed on the armature of the DC machine. Now conductors on the armature will be rotated by an external device called as prime mover. So prime movers can be a steam engine or a diesel engine or a water turbine. So magnetic field is provided by the field winding. Therefore, what happens here is, in order to obtain the larger number of output, we want several number of conductors to be joined in a particular fashion, and this several number of conductors joined in the particular fashion will form a winding. This winding will be placed on the armature, and the armature will be rotated by a prime mover. So that is how a armature is formed. Now magnetic field will be produced by the field winding. So we already understood about the armature and the field winding. Now what about the direction of the induced EMF? Now the direction of the induced EMF is given by the Fleming's right hand rule. So we have already seen this Fleming's right hand rule in the class. We will go through it again. So Fleming's right hand rule states that if the thumb, forefinger and the middle finger are held perpendicular to each other, then this middle finger will give the direction of the induced EMF or the current. So this gives the direction of induced EMF or the current. Middle finger will give the direction of the induced EMF and the current. Thumb thumb will give the direction of the motion of the conductor, and the forefinger will give the direction of the field. So what does the Fleming's right hand rule state? Fleming's right hand rule states that if the three fingers of the right hand, that is the thumb, forefinger and the middle finger, if they are held perpendicular to each other, then the middle finger will give the direction of the induced EMF, forefinger will give the direction of the magnetic field, and the thumb will give the direction of the motion of the conductor. So this is how you obtain the direction of the induced EMF. So this is about the working principle of the DC generator. Thank you.